All right, chemistry 3111 rather. Let's take a look at these questions. So we got a few. We got 19.30, 19.31, 19.32, 19.33, 19.34, 19.38. Okay, so we're going to go through all these questions right now before we get into the very last reaction in the whole chapter, which is the Baeyer vinegar. But the first couple questions here, I'm not going to spend an abundance of time on these because they involve the Grignard reaction, which is something that is near and dear to all of your hearts already. Remember that the second step for a Grignard, you can put water or you can put H3O plus. It's acceptable. Sorry, or H3O plus. It's not asking for any mechanisms in here whatsoever. If you want to write one in, it doesn't hurt, right? You're taking this ketone, you're treating it with ethyl magnesium bromide. So the ethyl carbanion is a strong nucleophile. Um, you're going to get the nucleophilic attack occurring like this. So you're going to end up with an intermediate that's going to look like this. I'll just use pH for the phenyl, just so I don't have to draw out the entire thing. So we end up with this. So we're going to have the original ethyl group. Then we have a second ethyl group. And then in the next step, we're going to protonate that with water or with H3O plus. It doesn't matter. Either one is totally fine. I'm going to write down H3O plus just to be cheeky here. So I'll put H3O plus. And again, I know it's not asking for a mechanism, but I am your instructor. So we're going to abstract a proton here, and then we're going to end up with our tertiary alcohol. So we end up with this product, where we have this, this, and this. So we have our two ethyl groups like this, and then we have our alcohol like that. So remember, we take a ketone, and we end up with a tertiary alcohol. Okay, and the next one we have an aldehyde. So remember, an aldehyde gives us a secondary alcohol. We have phenyl magnesium bromide. Again, I'm not going to draw the entire mechanism, but remember you have your phenyl carbanion, your Grignard reagent, which is going to be a strong nucleophile, attack the carbonyl. I'm not going to draw the intermediate this time. After protonation, what are we going to have? Let's see. We're going to have the first aromatic ring, right? Then we've got the carbon that's got the oxygen attached to it, and then it's going to have a hydrogen, right? I'm not going to leave that in there because this is a bond line structure, but then it's going to have the other phenyl, so another aromatic ring like this, okay? And then we have the hydrogen here after the proton transfer. So there you go. So when we have an aldehyde, remember, we get a secondary alcohol. And again, this is review. So both of these questions would have been fair game for quiz 12. So this is chapter 12 review. So there's nothing really new here, but it does bear repeating because we're talking about aldehydes and ketones. And so this fits into chapter 19. Now the next one, it's using Grignard chemistry again, but it's just kind of sprucing things up, asking a little bit more detail. So you can see that we're going from our first compound here, this is cyclopentanol, which has 5 carbons, to 1-methyl cyclopentanol. So this has a total of 6 carbons. And so in order to do this, in order to add this methyl group from a Grignard, we have to first oxidize this to a ketone. And so how many ways could we oxidize that to a ketone? The answer is many ways. You could use chromic acid, you could use PCC, you could use the Des-Martin periodinane. They will all work. Okay, I'm going to use the Swern this time. So in the Swern, we had DMSO and oxalochloride in the first step. In the second step, oops, I got DMSO on the brain. In the second step, we have triethylamine. So there's our Swern oxidation to give you our ketone. And then in the next part, we just have to use methyl magnesium bromide. So the first step is going to be methyl magnesium bromide, or you could have put methyl magnesium chloride. That's totally fine. And then in the second step, you can put H2O, or you could put hydronium, H3O plus. Either one is acceptable, and you end up with what? A tertiary alcohol. So you end up with the final product like that. The next one is virtually the same problem. Okay, you could use the exact same conditions again. We're going to take that alcohol, and let me just scribble it down here. So you're going to take this alcohol, and you're going to oxidize it, but we're going to oxidize to an aldehyde, not to a carboxylic acid. So we need a weak oxidizing agent. We could use the Swern oxidation again. We could use Des-Martin periodinane. We could use PCC. They all work. I'm just going to choose the Des-Martin periodinane in this case. It's going to give me the aldehyde. So this is cyclohexane carbaldehyde. And then to get to the final product, we're going to treat that with methyl magnesium. Instead of bromide, I'm going to choose chloride just to be different. And then I'm going to put H3O plus or H2O in the second step. And that's going to give me my secondary alcohol. So there you go. And again, and not to downplay the question. It's not a simple question. That's for darn sure. But just remember that this would have also been fair game for Chapter 12. Okay, this is just a review of Chapter 12, but it falls under the umbrella of Chapter 19. Why? Because we involve, ketones and aldehydes along the way. And so it's pertinent for this chapter. Okay, let's turn our attention to something new. And I told you that this is actually the best way to make a cyanohydrin, is to use potassium cyanide in HCl. So if you don't remember what a cyanohydrin was, okay, so a cyanohydrin is when we have a carbon that has like an alcohol and a nitrile on the same carbon. That's what a cyanohydrin is. And so after the first step, I'll use red ink since I have a red circle on the number 1, okay? We're going to end up with the cyanohydrin. So let's count our carbons carefully. So this carbon is going to be this one here. So now it's going to have an OH group, right? Because you're going to reduce the double bond down to a single bond, and you're going to have your nitrile on there. There's also a hydrogen on here. I'm going to leave that out because this is a bond line structure. And so if you remember, there's a couple of possibilities. We said we could treat this with lithium aluminum hydride, which is not part of this question. But if you do that, then you would reduce the nitrile to a primary amine. Okay, and then we also said that if you take it and you treat it with aqueous acid, so just hydronium, so aqueous acid, and cook that up, you end up with a carboxylic acid. So again, count your carbons carefully here. So we have our hydroxyl group. Did I put an extra atom there? Yep, there we go. So we have our hydroxyl group here. Okay, and then here we're going to have the carboxyl group from our carboxylic acid. So it's going to look something like that. It's not the best drawing. I guess maybe I should put this more correctly going straight up like that. There we go. That's a little prettier. But there you go. Give me a is everybody with me on these two? Or this one, I guess. Okay, so a cyanohydrin. So make sure you know what a cyanohydrin is. Very, very important. And I told you that we're going to look at this mechanism. So this mechanism, which is a doozy, is covered in Chapter 20. So you don't have to know this mechanism for this class, but you do have to know it for, you just have to know the reaction. All right, the next one. You can see that here, you notice that we have a carbon that has a hydroxyl and a carboxylic acid on it. So you can tell that that came from, right? That came from a cyanohydrin. So that means it came from this cyanohydrin where we have, let's see here, carefully. So we have our alcohol, and then we have this cyanohydrin, and then this one, maybe I'll use a different color. This one would have come from the same cyanohydrin. What do you know? It's going to come from this cyanohydrin as well. Okay, the one on top, we're just going to hydrolyze it with aqueous acid, and the one on the bottom, we're going to reduce it with lithium aluminum hydride. So we don't even have to write down intermediates. The first step to forming the cyanohydrin was KCN and HCl, right? That's the best way to form a cyanohydrin. So that's going to give you the compound in red. And then to convert that to the carboxylic acid, all we have to do is heat it up with aqueous acid, and you're done. Oh, I missed a step, didn't I? Okay, I forgot to oxidize this to a ketone. So let me just put a number 2 in front of this. Sorry, my mistake. So I'll put number 1. I'll just use PCC because I can squeeze it in there. Then we convert it to the cyanohydrin, and then in step 3, we're just going to treat that with hydronium. or aqueous acid, and we're going to cook that up, okay? The next one, same thing. I don't want to forget this time. I have to convert that to a carbonyl. So I will use, let's use, I don't know, you guys, students like PCC, so I'll try that again. Second step, to form the cyanohydrin, we're going to use KCN and HCl. And then in the last step, it's actually a two-parter. We're going to use lithium aluminum hydride in the first step, and then, oops, in step 4, we're going to use H3O plus or H2O. Either one is totally fine for the workup like that. Okay, so just keep in mind that the second step is the one that's going to give you the intermediate in red, and then the second step in this one is going to give you the intermediate in blue. Okay, so the first two steps are identical. All right, so a little more work on cyanohydrins, and we see how we can convert the nitrile into a carboxylic acid, in A, or we can reduce it down to a primary amine in the second one, in B. Okay, let's take a look at 19.34. This is a Wittig. This involves the Wittig reaction. So here we have a ketone. They gave us a symmetrical ketone, so we don't have to worry about E or Z or cis and trans and any of that stuff. Then they gave us this ylene form right here. Now keep in mind, that is in resonance with the ylide form. So if you want to practice drawing the ylide form, just draw your PPH3. Leave the double bond out. Put the positive charge on the phosphorus and the negative charge on the carbon. So if you remember my shortcut, when I kind of gave you my shortcut as to how to draw the product, here's how you do it. Draw the ketone or aldehyde. I'm going to draw the ketone. Then we're going to erase the oxygen. It's gone, okay? And now what we're going to do is we're going to attach up here, okay, where I have the letter C for carbon, we're going to attach everything that's attached to the phosphorus. So you can see it's got a total of 1, 2, 3 carbons. So I have 1, 2, 3 carbons. Remember, the first carbon is this one, okay? So that's the first carbon. So we have 1, 2, 3 carbons like that. Again, there's no E or Z to worry about in this case. So that's how you solve a Wittig reaction, nothing more than that. And it's going to be the exact same thing for the Horner-Wadsworth-Emmons. Now, keep in mind that with the Horner-Wadsworth-Emmons, you have a stabilized ylide. Okay, it's just baked into it. So for the Horner-Wadsworth-Emmons, we have a stabilized ylide. And when you have a stabilized ylide, you get the E alkene. Okay, that's something I would just say memorize that. Okay, there's no rationale for it provided in this class. It's way, way, way beyond the scope of our class. It would take me like an extra half an hour to explain that. Okay, so don't worry about it. Just kind of just memorize it. So we have this aldehyde. This is acetaldehyde or ethanal. Both names are perfectly acceptable. So here's what you do. The same thing as before. You draw the aldehyde. So we'll draw our aldehyde, which looks like this. Okay, we're going to erase the oxygen. It's gone. And now we're going to attach everything that's attached to the phosphorus. So this side over here. So what's it attached to? Remember that this carbon is going to be the first carbon here. Okay, so we have that carbon, and we have our ester over here like this, and you can see I'm missing a proton over here, but you can clearly see that this is an E alkene. And so I've drawn the product correctly. So it doesn't matter whether it's a Horner-Wadsworth-Emmons or a Wittig reaction, you just remove the oxygen and put in everything that's attached directly to the phosphorus. If it's a stabilized ylide, meaning one you could draw a resonance form for, in that case, you end up with the E. If it's anything simple like a methyl group or an ethyl group, in that case, you get the Z product, not the E product. All right, so there you go. So that's a little bit about the Wittig reaction. Okay, very, very important reaction. And the last one involves a Wittig reaction as well. And this is that question that I was telling you about. This is an ACS/MCAT/DAT type problem. They love this problem, okay? Where they give you some kind of unsymmetrical alkene, and they say, if you wanted to make this double bond using a Wittig reaction, how would you do it? Okay, you got two possibilities. Would you start with this as your ketone And then this, let's see here, pH3B. And this is your Wittig agent. So let me see here. Yep. Or I'll do this one in red. Or would you do it like this? You'd make the Wittig reagent from this. So you'd have this pH3 plus this is your starting material, aldehyde. So 1, 2, 3, like that. Okay. Which one of these would be the best route? Does anybody remember? Would it be the one in black or the one in red? There's one that's a lot better than the other. It's exactly. Thanks, Erica. It's the one in black, isn't it? Right? Because the one in black, okay. So this one in black, if you think about how do you synthesize this Wittig reagent, it's going to come from triphenylphosphine plus 1, 2, 3. So plus a primary alkyl halide, right? That's the SN2 reaction, that famous SN2 that I said you have to look out for. Okay, so you're going to get an SN2, but again, this is a primary alkyl halide. If you wanted to make the second one, okay, if you wanted to make this one here, okay, that would come from triphenylphosphine plus, I can try better than that, plus this alkyl halide, okay? It's going to work, but it's going to be really crummy because this is a secondary alkyl halide. And so the route in black is the one you want to take, right? So what our synthesis is going to look like, it's going to look like this. So we're going to start with, let me do it better than that. So we're going to start with our ketone. Let's start with our alkyl halide. So let me write it out here. So we're going to start with our alkyl halide, which is going to look like this, okay? The first thing we're going to do is we're going to treat that with triphenylphosphine. Then you need to treat it with a strong base. Now the base we use is N-butyllithium, okay? It's a very strong base and it abstracts the proton from the salt to give you the ylene or the ylide. In this case, they drew the ylene. So that's what I'm going to draw. So we get our ylene that looks like this. And then you're going to react that with the ketone, right? So we combine those together, and then you're going to end up with the product. So you're going to end up with this compound. There you go. All right, something like that. Okay. So I just realized I took up the entire dang slide. So what I'll do is I'm going to save this one for next class. Okay, we'll do this one next class. That'll give you a chance to try this on your own and, you know, practice the strong base, which is N-butyllithium. So our next class is on the 7th. So I'll put here the 7th. So we're going to tackle that problem. All right. Well, that's a lot of practice. But that brings us to the very last new reaction in this whole chapter. And that's called the Baeyer-Villiger oxidation. And the Baeyer is the same old Adolf von Baeyer with the famous, you know, barbituric acid and the started up the pharmaceutical company, the Bayer company and everything. Anyhow, I could keep going. But Baeyer and Villiger came up with this oxidation reaction. And this is actually something that you get, as an instructor, you kind of have to be careful when I say, oh, you can't oxidize a ketone any further. Well, technically you can. Okay, I think I said, well, maybe you can, but that's something we won't see until much later. Well, today is the day, okay, where you learn that you actually can oxidize a ketone and convert it into an ester. So here we're going from a ketone to an ester. And the way you do it is by using a peroxy acid. So if you don't remember, this kind of acid here, RCO3H, right, that would be the way you would draw the Lewis structure. Well, it's in here already, but it's like this, RCOOH, okay, RCO3H. That's called a peroxy acid. Okay, so I don't ask you to learn the mechanism of Baeyer-Villiger, so I'm going to put here will not ask you this mechanism. But boy, is it ever cool, okay? You get the nucleophilic attack by the second oxygen off of the carbonyl. Then you have a proton transfer, and then you have a really cool rearrangement. Look at that. Is that enough curved arrows for you at once? But anyhow, so you can see that you expand, right? This R group moves over. So we say that this R group, we have a word for it. We say that, and this is not a joke, okay? This is not something I made up. We say that it migrates, okay? We say that it migrates over to the oxygen. But the thing is if these two R groups are different, then you have to make a decision as to which R group is going to migrate and which R group stays the same, okay? And that's based off of something called migratory aptitude, okay? So if you have a cyclic ketone, it gives you a cyclic ester, and a cyclic ester has its own name. It's called a lactone, okay? So you can see here, this is called a lactone. Now, if you're wondering, okay, well, what about this migratory aptitude? How do I know which side is going to move if it's unsymmetrical? It's a good question, okay? Unsymmetrical, the rate of migration, and again, this is called migratory. If you want to Google it or something, you could say, you know, Baer-Villiger migratory aptitude, migratory aptitude. I'll just put aptitude. I like that. Anyhow, I've actually gone ahead and looked this up in a book a few years ago or something. I have a reference book in my office, and I was like, I wonder what are the factors that, you know, why is the migratory aptitude this, where the thing that's going to migrate the most would be a proton, followed by a tertiary carbon, followed by a tie between secondary and phenyl. If you're wondering, are you going to make me distinguish between these two? Obviously not, okay? Primary, then methyl. You have to memorize this for the quiz. So I would say here, memorize for quiz, okay? And then for the exam, I would say exam, maybe, you know, they might put it on an ACS or something like that, but I can't remember if I've seen it on there or not. But when I looked it up in my book, so you'll just have to take it for granted that I'm just reading this from my notes. This is what I put. Factors that control migratory aptitude are not completely understood, okay? The author is Laszlo Kurti, so L-A-S-Z-L-O-K-U-R-T-I, Laszlo Kurti. The factors that control migratory aptitude are not completely understood. So if you want to make that note, okay, we could put here, not completely understood. And that's why you and me and every other person who studies the Baer-Villiger reaction, we all have no choice but to kind of memorize the migratory aptitude. The one that I always find the easiest to remember is the proton, though. So if you ever have an aldehyde and you treat it with a Baer-Villiger, you always get a carboxylic acid 100% of the time. All right. So if you take a look at these ones here, if you take a look at this carbon, you can see that this carbon is attached to two carbons going away. This one doesn't count because it's sp2 hybridized. So we would say that this one is secondary, whereas this one here, I'll put this one in blue, this is a methyl. And you can see that secondary wins over methyl. And so the oxygen gets squeezed in here. So maybe I'll use black. So that's what your product is going to be. Obviously, you wouldn't draw it that way. You would draw it like this. The one on the bottom, you have a phenyl. So we have a phenyl, and then we have a proton. Well, the proton always wins. And so in that case, you end up, like I said, with a carboxylic acid. So again, you want to have this memorize for quiz. Come on. There we go. Something like that. So for the question here, I don't expect you to have the migratory aptitude memorized in 10 seconds unless you're, you know, some kind of Goodwill Hunting or savant or something like that. So what we'll do is this, is I'll just scribble it down here for you. So the migratory aptitude goes like this. So you have a hydrogen is first, followed by a tertiary carbon, followed by a tie between secondary and phenyl. Then you have primary, and then you have methyl as the bottom of the barrel, okay? So now that we have that in here, if we take a look at these two compounds, you can see you're treating both of them with a peroxy acid. I think this is one case where your instructor is going to buck the trend, and I'm going to do part B first, okay? Because on this side, on the left-hand side, you can see you've got a secondary carbon. You'd say this is secondary, but on the right-hand side, you've got a proton. So what kind of functional group am I going to get in my final product? Will it be an ester or a carboxylic acid? And it's not me trying to tease you or get you or something. What would it be? Remember, the hydrogen has the highest migratory aptitude. Exactly. You're going to get a carboxylic acid, right? So you're going to get something that looks like this. So you have your carbonyl here, and there you go, carboxylic acid in that case. So the oxygen is going to go here. The next one, or the one on top, this carbon is secondary, right? And then this one over here, this carbon is only attached to, again, going away from the sp2 hybridized carbon. This carbon is primary. So secondary wins over primary. And so our ester, in this case, is going to look something like this. So put our carbonyl, we won't touch this side. Then we have our oxygen, and then we're going to have our cyclohexyl group like that. There you go, my friends. Not too bad. There you go. A little bit about the Baeyer-Villiger oxidation, kind of a cool reaction. You know, if you think about the Baeyer-Villiger reaction, it is pretty neat. You know, I feel like the book doesn't really hammer on changes in functional groups, but you think about, you can take a ketone and convert it to an ester. You can take a cyclic ketone, convert it to a lactone. You can take an aldehyde, convert it to a carboxylic acid. So there are some pretty neat things you can do with the Baeyer-Villiger oxidation. Anyhow, kind of a cool reaction. So that covers all of the new chemistry in this chapter. Okay, we've covered all the reactions. I can prove it to you. We go down to the very bottom. Okay, so today, kind of going backwards, we covered the Baeyer-Villiger. That was number 13. So number 13 is the Baeyer-Villiger. Then we covered the Wittig. We also covered the Horner, Wadsworth, Emmons, which is like a variation on the Wittig. Then we covered cyanohydrins. We talked a little bit about Grignard today. That's nothing new to you guys. We talked about lithium aluminum hydride and sodium borohydride. Again, nothing new. And all the other chemistry that's on here, whether it's a hydrate, an acetal, a cyclic acetal, a thioacetal, an imine, an enamine, an oxime, a hydrazone, what else? Rainy nickel. We went over that. We also went over the Wolff-Kishner reduction reaction here. So we've covered everything in here, okay? But now we're really getting to the point in this class where the glass is starting to get pretty full in terms of reactions that you guys know now, okay? You know a lot of different reactions. And so you got to start kind of sorting it out in your brain, What are all the things I can do now? It says, if you're asked to do a synthesis, question number one, I would say, is always, is there a change in the carbon skeleton? Am I adding carbons, taking carbons away? And you can see now that we have new ways to add carbons, right? We used to use, the only thing we had when we first started out back in chapter 9 was using an acetylide or an alkanide as a nucleophile, right? Now you've got Grignards, you've got cyanohydrins, you've got Wittigs, and we're going to learn more. Okay, we're going to learn more as we move forward. Then you can ask yourself, well, is there a change in the functional group? Right? Do we have new functional groups? These are the kind of things we want to ask ourselves. We have literally learned how to do all of these transformations. Okay, all of these ones we knew before we even started this chapter. And now we've taken the ketone and the aldehyde and we've blown that open and we've learned a whole pile of new reactions in this chapter. So before, I'm going to review section 19.13 with you in a little bit, but I want to try some synthesis problems with you, okay? I want to try these 3 problems, and then once we solve these 3, we're going to take a look at, I just want to take a quick look at spectroscopy with you. I know you guys are all really good at spectroscopy, but I'm going to go ahead over to a blank just to make sure I have enough room to solve all of these, so just bear with me here. So I'm going to go down here. Come on. There we go. So this is 19.40. So 19.40. And the first one, we're taking methyl cyclohexane. Right. This is how I learned organic chemistry, just with a blank piece of paper. And I would just write down the starting material, product, and then I would start to cry. No, I'm kidding. and start to be very puzzled about what should I do next, right? Okay, so let's think about this. You can see that we're adding one carbon. Right here we have 7 carbons, here we have 8 carbons. But I can see, I don't know about you guys, but what I see in terms of a retrosynthesis is this. What we need to make is this compound. We need to make 2-methyl cyclohexanone. So we need to make this compound. We need to put a carbonyl at this position, okay? Where I just put that blue carbonyl. Because to get from here to here, all I have to do is treat it with methyl magnesium bromide. So now the question becomes, well, how do I get from here to here? Okay, how do I get from there to there? Well, you guys know, and I know, that if I started with methyl cyclohexane, an alkane, as my starting material, there is literally one reaction that we know that we could do. Could anybody tell me what that reaction is? What is the one choice that I have here, besides burning it, which isn't the answer? We're not just going to burn it and walk away. Burn it and go home. Does anybody? Yes, absolutely, you guys. Thank you. It's bromine and light, right? If I treat that with bromine and light, hey, it must be right. Okay, don't second guess yourself. You know this has to be right because it's the only thing we've got. Okay, but you can see that now I could do an elimination to make the Hoffman alkene or the Zaitsev alkene. And if I made the Zaitsev alkene, so let's say I made the Zaitsev alkene, it would look like this. Then I could just do an anti-Markovnikov addition of water across that double bond and then oxidize it, and then I would be at this compound. So could anybody tell me to go from here to here to make the Zaitsev product? So I'll just write here, this is the Zaitsev. Would I use a hindered base or a non-hindered base? Unhindered base is the proper term, I guess. Would I use a hindered base or an unhindered base? So for this one, I would want to use an unhindered base. Exactly. I would want to use sodium methoxide. If I used a hindered base, okay, like t-butoxide, so if I did that, if I use potassium t-butoxide, that would give me the Hoffman product, which would be the less substituted alkene. So that would give me the Hoffman. Okay, so I want to make the Zaitsev product because then I can do an anti-Markovnikov addition of water, so borane DHF, followed by hydrogen peroxide and sodium hydroxide. And that's going to give me the alcohol I want, okay? And then to oxidize that alcohol to the ketone, what am I going to use? I'll just use PCC, okay? Then what I'll do is I'll change all this to black, okay? There we go. And so to finish it out, what do I have to do? I have to add, in step 1, I'm going to add methyl magnesium bromide. And in step 2, I'm going to add H3O plus or H2O, and that's going to protonate to give me my tertiary alcohol. So how many steps is this overall? It's a total of 1, 2, 3, 4, 5, 6, 7. So 7 steps to get this thing done. So that's not trivial, you know, a total of 7 steps, right? There you go. It's a 7-step program to get from what would you call that? Methyl cyclohexane to what? 1,2-dimethyl cyclohexanol. All right. Here we go. Let's try the next one. Let's try the next one. So this is 9. Let me move down here. This is 19. Where's my pen? 19.40. This is B. And it looks something like this. So I guess this is his favorite starting material. Come on, Mr. Dion. You can draw better than that. There we go. Methyl cyclohexane. And then we're busting the ring open somehow. And we're making this compound. So 1, 2, 3, 4, 5, 6, 7, 8. I think I have that right. So I have a hydroxyl group here. What else? And I've got a carbonyl over there. Okay. Well, let's see here. We're starting out with a total of 7 carbons. We've got 7 carbons here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're adding 2 carbons to this thing. And we're opening the ring somehow. So we know the first thing has to be this, right? We know the first step has to be bromine and light. There's nothing else we can do. And so that's going to give me, oops, that's going to give me this compound, right? Now, in terms of breaking the ring open, really the only thing I have is to have, right, is to have a double bond in the ring and then to treat that with ozone, followed by DMS, right? Because that's going to open the ring. I'd get 1, 2, 3, 4, 5, 6, and then I'd have a carbonyl over here and a carbonyl over here like that. And you can see that you have 2 carbonyls in the compound. But instead of having, if we were to do this, if we could make, right, if we could make this compound again, which we can, okay, the same compound we did in the last problem, if we busted that open with ozone and DMS, what's it going to look like? Well, we're going to break the bond right here. So let's count. We have 1, 2, 3, 4, 5, 6, 7. So let's write that down. 1, 2, 3, 4, 5, 6, 7, like that. On carbon number 2, I'm going to have a carbonyl. And then on carbon number 7, I'm going to have a carbonyl like this. So I've got a ketone and an aldehyde. So now if I think about taking this group and getting to here, and if I think about this group and getting to here, what do they both involve? They both involve the addition of methyl magnesium bromide, right? Because that's going to add my 2 methyl groups. If I had excess methyl magnesium bromide and then I protonate, but in the where the blue circle is, I'm going to end up with the right group. I'm going to end up with the alcohol. But in the green circle, I'm going to end up with a secondary alcohol, but I could oxidize that using PCC because a tertiary alcohol will not oxidize, okay? So if you don't follow what I'm saying, watch this. So if I take this compound and I treat it with, in step 1, excess, meaning a whole bunch of methyl magnesium bromide, and in step 2, I use water or hydronium, I'm going to end up with this. Let me write it down carefully. I'm going to erase this ring because it's taking up valuable real estate, okay? Oops, I didn't mean to do that. There we go. I'm going to end up with this compound. So 1, 2, 3, 4, 5, 6, 7. Son of a gun. Let me move it so I have more room. Let's see, 1, 2. Okay, hopefully I kind of squeezed it in there like this. So that's going to give me my tertiary alcohol. Now I'm going to have a secondary alcohol here. Okay, now I didn't give myself enough room. Tell you what I'll do. I'll move this over here like that, and I'll move this over here, and we'll change this arrow. Let's do this. There we go. So now to get from here to here to the final product, all I have to do is oxidize with PCC, and that's going to oxidize this secondary alcohol, which I'll spruce up a little bit. It's going to oxidize it to the methyl ketone, and the other one is not going to oxidize. Okay, so there you go. That one's a little bit trickier, but still a good problem. Let's try one more, and then we'll take a look at spectroscopy, and we'll take another break. So this is 19.0C. We're starting with, this is called methylene cyclohexane. So this compound here, and we're going to make a, what is it? It's an imine. Okay, so we're making an imine. And if you understand imine chemistry, I don't like to make anything sound simple in this class because nothing in this class is simple. Okay, but if you understand that this is an imine, you can do a retrosynthesis pretty quick. You can say, well, I'm going to make the imine when I make this double bond when I make the imine, and what's that going to come from? Right? That's going to come from, it's going to come from this aldehyde. So I need this aldehyde, and I need this primary amine, isopropylamine. So the isopropylamine, we're just going to assume that we have that. So the question becomes, well, how do I get from here to here? Well, that's actually pretty quick. That's a 2-step process. The first step is actually 2 steps, but we're going to do anti-Markovnikov addition of water across that double bond. So that's an old reaction that we learned way back in chapter 8 of organic chemistry 1. So that's going to give us the primary alcohol. Then we can oxidize that. Let's use the Des-Martin periodinane in dichloromethane. And that's going to give us cyclohexane carbaldehyde, this compound. So then to get to the imine, the Schiff base, what do I need? I need the amine, which is, this is called isopropylamine. The name isn't important. We haven't learned amine nomenclature yet. I need a catalytic amount of acid. And if you want to write negative H2O, I think it's a good idea to do that to remind yourself that you're losing water in the process. So that would be what? A total of 4 steps to do that one. So that covers 19. So we just did 19. 19.40 A, B, and C. Okay, check-a-roo on all of those. So I just want to take a quick peek at spectroscopy with you, because I know a lot of you are working on spectroscopy currently with Mr. Geiger. So if I go down to the bottom, okay, so we covered this. We talked about synthesis strategies. We solved those problems. And just to remind you of a couple of things with respect to aldehydes and ketones, if you don't remember the carbonyl stretch, and this is a question that I've seen come up on a final exam before. Let's say you have the carbonyl stretch of a ketone, like this one is at 1715 centimeters to the -1. Once you conjugate it, right, what that does is it weakens the bond. It's got the double bond. This double bond has more single bond character, okay? And remember that wave number was proportional to the strength of the bond, the force constant over the reduced mass. Okay, this is a greatly, I mean, it's technically the square root of all this, but this is a greatly simplified version of the formula that you would have learned in chapter 14. But the bottom line is that wave number is inversely proportional to the bond strength. So the force constant is related to bond strength. And so when the bond is conjugated, it weakens it. So this is going to be a weaker double bond because of more resonance structures. And so it's going to have a stretch at a lower wave number. Conversely, I don't remember if we talked about this or not in chapter 14 of Organic 1, but if you have a strained ring, the more that the ring is strained, rather, you end up with a higher wave number. So you can hear with cyclobutanone, it's all the way up to 1780. Also, aldehydic stretching. So this is called aldehydic CH stretching. So what that means is when you have an aldehyde like this is one of the most distinct absorbances in all of organic chemistry in the IR, is that you see 2 stretches. To me, they're usually around 2750 and 2850 centimeters to the -1, but just 2 small stretches in that range for aldehydic stretching. So here you see aldehydic stretching. This is pentanal, so pentanal, or valeraldehyde. Both are perfectly acceptable. So you see the carbonyl, right? This is the carbonyl stretch, but then these are the aldehydic stretchings, okay? So this is aldehydic stretching. Anyhow, what else do we see here? Protons next to a carbonyl are going to be deshielded by the carbonyl by 1 part per million. So we went over that in chapter 15.5. There's a whole table that goes over this for you. And then if we have an aldehyde proton, that's one of the few giveaways in the NMR. If you have a proton at like 12 parts per million, that's going to come from a carboxylic acid. Okay, that's the proton from a carboxylic acid at 12. But if it's at 10, it's from an aldehyde. So we see here also the carbonyl carbon. So if you have an aldehyde or a ketone, the carbonyl carbon is going to be, so aldehyde or ketone, carbonyl carbon is somewhere around 200 parts per million for this carbon. All right, so that covers all the material in chapter 19.